Okay, so now we are going to do the MDP question. So the first we are asking, if I'm trying to specify a 3-horizon policy for this problem, how many different policies can we choose from? So remember that this is a finite horizon MDP. So a 3-horizon policy basically means I need to say what is the action to do with 3 steps to go, with 2 steps to go, and with 1 step to go. Okay, and the 0 steps to go, essentially there is no action to make, so essentially you don't count that. And so in essence you need to say what action to do in each of these states A, B, C in 3 different scenarios. Scenario 1 where there are 3 steps to go, scenario 2 there is 2 steps to go, scenario 3 there is 1 step to go. Now consider any one of them. Let's say scenario where you have 3 steps to go. The number of policies would be, in A you can either do left or right, there are 2 possibilities. In B you can do left or right, 2 possibilities. In C you can do left or right, 2 possibilities. Okay, and since they're all essentially, in the worst case, they can all be independent, so the number of possible policies would be 2 cube, that is for 3 steps to go, times 2 cube for 2 steps to go, times 2 cube for 1 step to go. Okay, which would be essentially 8 times 8 times 8 number of policies. Okay, are basically equal to 2 power 9. Okay, it's equal to 512 number of policies. So the number of policies just for this little problem with 3 horizon is 512. Okay, that's the deal. Okay, the second we are asking is, if I told you the policy, and in my current policy 1 step to go, the action to do in B is to go left. Okay, then what is the value of B with respect to this policy? So the value of B with respect to 5 and 1 step to go is, of course, R of B plus what you get by doing the action go left. Okay, now doing the action go left, if you see, if you do go left 0.8, you'll get to A. So with 0.8 we'll get V0 of A, and then 0.2 you get V0 of C. Now V0 of A is just 2 because the 0 steps to go, the value of the state is the same as the reward, and then similarly V0 of C is 3. So that basically, and then of course R of B is -2, so this is -2 plus 0.8 times 2 is 1.6 plus 0.2 times 3, 0.6, which is -2 plus 2.2, which is equal to 0.2. So the value of B with 1 step to go, if you are essentially doing this policy, which actually tells you to go left, is 0.2. Now if I want to do what I want to do next in the last part is to find 1 step to go value, optimal value. Okay, so if I want to do the optimal value, in a sense you have to realize that the V of B 1 step to go, there is no policy here, V of B 1 step to go would essentially be R of B, of course, okay, plus max of what it does by going left and what it does by going right. Now we know that going left is, of course, from here we know going left is 2.2, and for going right I just have to notice that if it went right with 0.7 it will be in C and 0.3 it will be in A. So that means for going right you will get 0.7 times the reward of C is 3. Reward of C is 3 plus 0.3 times the reward of A, which is 2. Okay, now what that means is this is 2.1 plus 0.6 equal to 2.7. So I have to take max of going left and going right, and since 2.7 is bigger than 2.2, I'm going to take this and then add it to R of D, which is minus 2, and then that will be minus 2 plus 2.7, which is 0.7. Okay, now of course the action, optimal action, of course, for one step to go, in B is whichever is the max that you got here, which is go right. That's it. Okay, that's all.